So I'm doing standard 0.3, which is matrix operations. I'm doing question 2, which is talking about the trace of a matrix A. And so the trace of a matrix A equals the sum of the numbers on the diagonal. And also the trace of a matrix A equals the sum of the eigenvalues. So part A wants you to prove that the trace indeed gives the sum of the eigenvalues of a 2 by 2 matrix. So here I defined my matrix A as A, B, C, D. And then so the trace of A, which is the sum of the diagonals, is just going to be A plus D. And so the next part, I wanted to find the eigenvalues. So to find the eigenvalue, you take the determinant of the matrix A minus lambda times the identity matrix. And the identity matrix is just ones down the diagonal, and all the other numbers are 0. So when you do that, applied to this matrix up here, you get the determinant of A minus lambda, B, C, and D minus lambda, and that equals 0. So then, to find the determinant, you just take this times this minus this times this. So that gives you A minus lambda times D minus lambda minus B, C equals 0. And then you FOIL that out and you get lambda squared minus A plus D times lambda plus AD minus BC. And then you can use your quadratic formula to find your eigenvalues. So the eigenvalues are A plus D plus or minus the square root of A plus D squared minus 4 AD minus BC. And then that divided by 2. And then, so there are your two eigenvalues. So now you add them together, and all the square root cancels out. So you're left with 2 times A plus D over 2, and the 2's cancel out, and so you're left with A plus D, which is the sum of the diagonals. So the next part wants to prove that the determinant gives the product of the eigenvalues of a 2 by 2 matrix. So if we say our eigenvalues are lambda 1 and lambda 2, that means the product of them are going to be lambda 1 times lambda 2. So next, you're going to act like you're solving for the eigenvalues. So you say the determinant of A minus lambda times the identity matrix. And then when you do that, you're going to get minus 1 squared times lambda minus lambda 1 times lambda minus lambda 2. And this is just the solution to a second degree polynomial. And these lambdas are just variables or coefficients that can be anything. So you can set those equal to 0, and that leaves you with determinant of A is equal to negative lambda 1 times negative lambda 2, which is just lambda 1 times lambda 2, and that gives you what we wanted to solve for. So the next part is we're using this matrix, this 3 by 3 matrix, and proving that both work. So first we want to find the sum of the diagonal, which is just 1 plus 1 plus 1, which is 3. Now we want to find the eigenvalues. And to do this, we can just plug the matrix into Wolfram Mathematica, like right here, and then when you click on it, these bars give you different options, and you can just say eigenvalues, and it pumps out the eigenvalues here. So then now you want to add them together, and so 1 plus I plus 1 minus I plus 1, the i's cancel, and that gives you 3, which is the sum of the diagonal. Next, we want to find the product of the eigenvalues and show that it equals the determinant. So Mathematica can also find determinants, and right here we see determinant, and so it solves and it says the determinant is 2. So now we want to multiply the eigenvalues together, and the eigenvalues were 1 plus I times 1 minus I times 1. And then when you do that, you get 1 minus I squared plus I minus I. And so plus I and minus I cancel out. Minus I squared becomes just 1, positive 1. So then it becomes 1 plus 1, and you're left with 2, which is the determinant. And that's the end of the problem.